Section 4.2 is called DC generator. And what it's going to show us in this section is we're going to take that same machine that we saw in section 4.1, internally constructed the same way. Only thing we're going to alter is the output of that generator. We're going to change this connection to the outside, to the load, through a device called a commutator. And that commutator is a physical, mechanical device that, by its construction, converts an AC voltage waveform to a DC voltage waveform. Now, when we were looking at the AC generator, we had this construction where we had these slip rings connected to brushes, and then we were able to connect the load through the brushes and take that outputted voltage. It ended up being an AC output, right? Looks kind of like this. And we could take that AC output to the load. Now, I want you to think about something here. As this coil is rotating through, and we said it was rotating through at 60 RPMs or 1 cycle per second, as the rotation occurs, and since there's a direct connection from the particular coil sides to these brushes, right? So this one is connected here and this one is connected there. What happens is the respective brushes, X and Y, as this thing rotates, they change polarity. Now, if we could figure out a way such that these brushes never changed polarity and they always stayed the same as this coil rotated through, then what we would have in that situation is a DC generator. And let's see how we can make that happen. Now, this is kind of subtle and actually very simple, but I think that makes it very, I think it even makes it more interesting. Everything else is the same. You know, here's our north pole of our permanent magnet. Here's our south pole. Here's our coil of wire, you know, that we're rotating through. You know, so everything's the same. Here's the load. The load's the same out here. Everything's the same, except if we go into some detail and we look at this thing. Well, I want you to think about this. This is called a commutator. And this is a solid piece here in the orange that I'm outlining, you know, and it's conductive just like the slip rings. And this is also solid and it's conductive, you know, say it's made of copper. Well, between those two solid conductive points in here, there is another section that is not conductive. So basically what you have is a section here and a section here, and it's separated by these two non-conductive segments. Okay, so just hold on to that for a second. And then the other thing I want you to plant in your brain is this idea now that instead of this coil, actually, let me erase some stuff here so I can try to show this to you. Now, as this coil is rotating through, in the AC generator, this conductor was rotating internal to the slip ring. Okay, and there, you know, and what it looked like, let's go zip back to this. This was turning inside of the slip ring as the coil rotated. Well, now what we have is a different thing altogether, in the sense that this whole commutator is rotating. And think about this. This coil A, it's permanently attached to this coil segment here. Okay, it's not free to rotate in there. This whole thing turns. This whole circle, this whole cylinder turns. And this coil is always connected to the same point on this half of the segment that it's attached to. Okay, so that's a different thing than we saw with the AC generator. Now, what makes this work the way that it does, and I wish I had more slides and figures that could walk us through, a complete rotation, but let's just do the best we can with what we got, right? And I want you to imagine this coil rotating through 90 degrees so that now this side D would be here and this side A would be here. And what would that look like physically on this commutator is that this segment here would be underneath brush X, right? As it rotates through, that commutator segment right there would be under brush X. And since it doesn't conduct, there's no voltage there. And of course, this segment here, rotated 90 degrees, would be here, and it would be at this point here on brush Y. So as this thing rotated through its first 90 degrees, we reach a point to where the connection points are the two commutator segments. And at that point, we've gone to 0. All right, so hold that in your mind just for a second, and let's go to the next stage here. Okay, now stick with me. So this coil has rotated 90 degrees. The coil segments that are non-conducting are at brush X and brush Y. Now, the polarity of the voltage that's generated is determined by the direction of movement and the direction of the magnetic field. Okay, now when we were looking at side A, it was moving down through a magnetic field that was oriented the way that we have here. Okay, now this thing rotated through 90 degrees, and so side D is here now and side A is here. And as it starts to rotate down through the magnetic field, again, side D now is going down through a magnetic field that's oriented this way. So what happens is this brush is going to maintain the same voltage because the entire thing is turning now, right? This whole thing is rotating through. So what happens is that this brush X never goes negative. Unlike the AC voltage that was generated, it never goes negative because of the way that this thing functions. So think through it, right? Side D going down now through a magnetic field in this direction, whatever that voltage level is, it's going to be the same as when side A was going through there. And since this whole thing rotates through there, the polarity never changes. All right, now what does that look like? Well, it looks like this. Here's our rotation, and say this was side A going through, and then, it gets to this point, 90 degrees. This is where the commutator segments are aligned with the two brushes, X and Y. And now here is side D going down through the magnetic field in that same orientation. Well, notice that it never goes below 0, and it starts to become positive. Think about side D at this point, and it's small at first, and then it starts cutting more flux lines. So it starts, positive and reaches another maximum until you get to, a rotation through of 90 degrees. Then it changes as it rotates through, and then you reach another 0 point and back and forth. But what happens, what's neat, and what makes this commutator do what it does is the whole thing turns and the brushes never change polarity. They always maintain the same polarity through that. Couple of things here, you know, as we look at this, due to this constant polarity between the brushes, the external load always flows, the current, excuse me, because of this construction, the current that flows through this load never changed direction. When it was an AC voltage, you know, it would be going this way for half of the cycle and through this, the second part of the cycle. That's an AC voltage. But for the DC voltage, because of this commutator, the current never changes direction because the polarity never changes.